Hello, my name is Chris Rakakis, and I am a research affiliate at MIT, also the Director of Modeling and Simulation at Julia Computing, and also Director of Scientific Research at Pumas AI, a pharmacometrics firm. So what we're going to be talking about today is scientific machine learning, differentiable simulation, and how this then can relate to things like astroinformatics. So what I really want to dig into first, though, is what is scientific machine learning? So scientific machine learning, right, is this domain that people have been starting to talk about, but why has it gotten buzz? Well, the main reason why it's gotten buzz is because it seems like it can do a lot of things where standard machine learning cannot. So for example, let's take a look at this case here, right? So here's actually a case. We're going to go into more detail in a second, but in this case, what happens is here's the training data, right? So the training data are these black dots. The blue waveform is the true waveform. The orange one is the learned one, and you can see just by having a little bit of training data, it's able to extrapolate into the future and get almost would be a perfect fit, right? And what people always talk about, like machine learning will not extrapolate out of data and et cetera, but here's a case where it looks like something that's machine learning like is doing that. So why is this breaking your assumptions? Why is this doing something different from standard machine learning? And how can you solve similar problems? And what is going on, right? So that's what I really want to talk about here. What is special here? And what is special is really this idea of let me move this over here. What is special is that machine learning is not just about data, right? Or scientific machine learning is not just about data. So when people talk about machine learning, you're always talking about hey, if I have this Google-sized data set of 1 billion terms, then I can make a good prediction on how people are going to talk about language, or how Alexa is going to interpret language, or how you do a Google search, right? But what we have as information, right, is not necessarily just data. In science, we have a lot of other information, and this information is captured in models, right? So, for example, you have a lot of cases where, for example, general relativity, right? What is the data set that you would point to that says that general relativity is correct, and then you train a neural network on to teach it general relativity, and you go, well, maybe there's a lot of different data sets that capture little parts of it, but the theory of general relativity is something that encompasses thousands and thousands of different simulations, right? So, and there's thousands and thousands of data sets that have been found to be compatible with it, right? And so, in some sense, if you just gave someone Einstein's equations, that would be more information than just the measurements of a few stars out there, or measurements of a black hole, of stars rotating around a black hole, right? In theory, if you have enough data, it would capture the same amount of information. But in practice, in a lot of cases, models have more information than entire data sets. And now, this is the reason why a lot of people do, physical modeling and, develop physical theories from first principles and then prove that these theories work, right? This is why, physical theories seem to extrapolate so well. This is why a lot of people always go back to them. But now what scientific machine learning is doing is it's saying, can we come up with forms of machine learning that use the models as a basis and mix this with the data, right? Because there's completely data-driven algorithms, right? There's train a neural network on the data and see what it predicts, and then there is this world of, well, my model's really good, so let me use my model. But is there a combination between them where, say, your model might be missing information, but you can complete it with data and you get good predictions, even though with that amount of data, a machine learning method like a neural network would not be able to give a good prediction on its own. So scientific machine learning is about this combination of methods. And so, what I'm going to talk about is twofold here. First, I'm going to talk about scientific machine learning applications. What are some problems that have been solved by scientific machine learning? And then we're going to go into the software kind of, software mathematical kind of world where we're going to really discuss, what is the mathematics behind the methods of scientific machine learning? What's interesting about it? What should you know about it? How does that inform the different methods that are going on? And how does that inform, someone who's potentially interested in the subject, how things work, and what things you need to be aware of. So the first method to talk about is the physics-informed neural network, because this is dead simple of a scientific machine learning method, you can immediately see some pretty good results. So what is a physics-informed neural network? Well, physics-informed neural network is a method which is, physics-informed neural networks is a method where you take a physical equation, say a differential equation, and you represent its solution as a neural network. So here, for example, we say let's say we had a partial differential equation, right? This partial differential equation takes in a point in space, x, and a point in time, t. We send it through the neural network, and it spits out what the value of the part of the PD solution is at that point, right? And now, how do you know whether something is the solution to a differential equation? Well, you know that something's a solution to a differential equation if when you take a derivative of it, it satisfies some constraint. Like an ordinary differential equation is you take one derivative in time, right? And that should be equal to some function that right? U prime equals f. The heat equation is that one derivative in time equals two derivatives in space, right? That's what the heat equation is. And so if you have some function representation of the solution, you can just take derivatives of it, right? So here's a neural network. It takes in x, it takes in t, it spits out u. You take two derivatives of it with respect to x. You take one derivative of it with respect to t. And those two things should be equal if this u right here is a solution to the heat equation. And so then you just enforce it through the loss function that two derivatives of delta of derivatives by x should be minus one derivative by time. That is a loss. You sum up the total loss, and if that loss goes to 0, then this u is something where two derivatives in x equals one derivative in time, and thus it is a solution to a differential equation, right? And that's really the key, right? So whenever you're solving these physical equations, right, you write down relationships that have to be true. And what a neural network is at its core is just a universal function approximator, right? So what is a universal function approximator? A universal function approximator is something that can approximate any Rn to Rm functions given enough parameters, right? So a neural network satisfies that, right? It, from R2 to R1, this neural network can be any R2 to R1 function if you have enough hidden layers and if your hidden layers are large enough, right? So that's something that you can prove. So the way that scientific machine learning is using neural networks is not necessarily as a data method or something like that, is using it as a function approximator, right? This neural network is a way of representing any possible function of x and t. So let's make u be any possible function of x and t, and if it needs to satisfy some criteria on the derivatives, you can see how close it is satisfying that by taking derivatives of the representation you have. And then you just move around your parameters until your representation of the solution gives you the property that you want, right? And so that what I described right there is not completely scientific machine learning, right? That's just using a neural network to solve a differential equation, right? That is just, if you do this, you will get a neural network that satisfies all the properties of the differential equation, and therefore the neural network is the solution to the differential equation. Now, to make that then be something that is not just solving equations, but actually being a piece of for scientific machine learning, is what you would do is you would add a term to this where you say, well, I'm also going to make sure I match data, right? So you can have a physical equation that's encoded in your neural network, right? You have one loss term that's like, my boundary conditions, my initial conditions, and my partial differential equation should be close to satisfied. But then you have another term that just says, well, but also the neural network at x and t should be equal to this value because this is a measurement that I have. And so you can add those two pieces together in the loss function, right? You can weigh them however you want. You put a lambda in here to kind of describe how much the PDE solve should be weighed and how much the data should be weighed. But you piece these two together, and now you have a system that simultaneously solves a differential equation but nudges it closer to your data. And this is what the physics-informed neural network technique is. So what does this look like? So there's a lot of different software that can do this now. Here's one that's called neuralpde.jl, and you can watch the whole video from JuliaCon 2021 on this. You basically just put in your differential equation in a symbolic form, right? So you say, like, here are my parameters, here are my variables, here's my differential terms, and what do I want to be satisfied? I want two derivatives in x plus two derivatives in y to be equal to this sine function, right? And so what it will do is it will then then you define a neural network, and then you say discretize, and you solve it with an optimization. And what it does is it takes this equation and imposes it onto that neural network. It says, okay, two derivatives in x plus two derivatives in y should be equal to this function over here. At each point in space, it samples in space, and that's how it gets a loss function. Like, how close is that to being true here? How close is that true to being here? And that's a loss function. And then after it does some optimization to find the parameters of the neural network that satisfy that loss function, it gives you a neural network which generally satisfies this equation, right? So it's a neural network that takes in x and y, spits out a value for what it thinks u is. And so then it will give you something that when you double check it, it is a solution to the partial differential equation, right? So that's the core of the method. And you can also then say, in this kind of framework, you can say, add an additional loss function that measures the distance from its measurements between my real data, right? So you can then do this in that scientific machine learning sense. Now, why would you use a physics-informed neural network instead of just using any other neural network? Well, the main reason is because physics-informed neural networks, they tend to outperform standard machine learning. So here's a nice example of this, right? So on this harmonic oscillator, you can see that here's our data, right? And when you no longer have any training data, right, the physics-informed neural network will just kind of the standard neural network will generally not be able to predict what happens outside of its data set, right? So it trains and it learns, okay, this is how things are moving, and then you ask it what's going on in the future, and it goes, you gave me no data about the future. I'm just going to do something fairly random, right? It's hard to know even what the neural network will do, right? It just kind of picks a behavior because there's no data that would constrain its behavior. Doesn't mean the neural network hasn't learned anything, right? It has learned good predictions between your data points, but it has not learned what to do outside of your data set, right? Whereas what happens with the physics-informed neural network is it has two pieces of information, right? It knows, say, I'm solving a harmonic oscillator, but you have real data points that says, this is not just a harmonic oscillator, but it has some dampening to it. And when you mix those two loss terms, right, even though you don't know the full equation, right? In this case, the physics loss that you give it is the undampened harmonic oscillator, but you give it data points from the dampened harmonic oscillator, and it's able to predict in the future, down this time series, how to extrapolate out how that dampened harmonic oscillator will work, right? Right, and it seems a little bit magical at first, but if you think about it in terms of amount of information, I think that it kind of comes together, right? Because you've given it the information that it's something harmonic oscillator like. You've given it enough information that if you knew the full model, this would tell you that it's not an undampened case, but it's actually a dampened case. And so it uses those two things together and extrapolates in a way that is the simplest extrapolation in some sense. It's like the Occam's razor extrapolation is to think, this must be a dampened oscillator with this dampening, and it basically pushes it forward from there. Now, the reason that it matches the most simple model in the Occam's razor idea, that's still something that's being proven in the community and such, but that is something that kind of you could empirically show occurs in a lot of cases. So why use a physics-informed neural network? Well, because it can outperform just standard machine learning if you have some prior information, and of course, in a lot of cases, you have a lot of good scientific theories, right? So if you have a scientific theory that's approximately true, you can slap it in there as a piece of information to kind of grow the predictive power of your system, right? The nice thing about physics-informed neural networks is that it really generalizes easily. So if you have, so you have u of xt, right? You can evaluate it at any point. And so let's say you want to do physics-informed neural networks on cases with integral differential equations. You just take an integral of u, and you have the integral, right? And you can check the loss function there. Let's say you want to do this with fractional differential equations. You take the fractional derivative of u, just numerically approximate it. What happens if you want to do this with the delay differential equation? Well, you can evaluate u at any time point, so you can delay it, right? Making this work for any partial differential equation, any differential equation, taking this idea and bringing it to there is rather trivial, right? You just use the fact that you have a representation of the solution, and you stick that representation of the solution into whatever equation it's supposed to satisfy, and how far away it is from satisfying it is the loss. So there's really not much to make it generalized, and it's very simple, right? I mean, you just define a neural network, you define derivatives, and you just plug them together. So your simplest machine learning framework will be able to do this. But the main reason to not use a physics-informed neural network is performance. Physics-informed neural networks are notoriously very slow. There are some papers that don't say that they're slow, but I'll address that at the end. So kind of going down this line, then what are some other methods in scientific machine learning? And the next one that we're going to do, and we're going to spend a lot more time on because it's a lot more complex in its methods and implementation, is the differentiable simulation approaches with universal differential equations. So what exactly is this? So what we do with universal differential equations is we define a differential equation in part by a neural network, right? Why do we do it with the neural network? Well, once again, what we're using is this universal function approximator idea, right? What we want out of a neural network is that it can approximate any possible function. So if I had a model, say I had a model of rabbits and wolves, and I knew that if you leave rabbits alone, they grow exponentially. If you leave wolves alone, they die exponentially fast, right? That's the two pieces of information I have. How do rabbits and wolves interact? Well, that's some function that I didn't put in my model yet, right? And how do you represent any possible function that you haven't put in your model yet? Well, you just add a neural network, right? That's about all it is, right? So, if you need something that's an R2 to R2 function, then you make a neural network that has 2 inputs, 2 outputs, and as many, hidden layers as you want. The number of hidden layers needs to go to infinity to really actually represent any possible function, but, you cut it off at a finite number so that way you're epsilon close to any possible function, and now you have a representation of all possible models. Right, but it's not just representation of all possible models. It's all possible models with some kind of inductive bias towards the science that you do know, right? And so that's what the universal differential equation is. And so if the way that this is used is you can take your measurements. So you take a model that you take your measurements, and you basically fit your differential equation to this by doing a parameter estimation, right? You treat these neural network weights as a part of the parameters. And once you have learned the neural network weights, the nice thing here, right, is that you actually are learning the model, not its solution. Right? And that's a key difference from the physics-informed neural network, right? Remember that the physics-informed neural network is doing the neural network on the solution to a set of differential equations, or the solution of physical laws. Now, the issue with doing that is that the solution to physical laws may not have easy representations, even though the equations themselves are simple, right? So, for example, think about the three-body problem, right? The three-body problem is just standard Newtonian gravity, and standard Newtonian physics with gravitational potentials. Writing that down is something that a high schooler can write down a three-body problem, right? In terms of the differential equations involved. But the solution to the three-body problem is not representable in any, with any kind of elementary functions. It's actually one of these known chaotic systems. Its solution can generally fall on a fractal, and there's no easy representation of this, right? So if you're trying to make your neural network represent the solution to a differential equation, it's necessarily going to be it's necessarily generally an object that is not easy to represent, right? Now, if you're making your neural network represent things in your model, for example, right? So, physical models are generally simple, and so what you can also you can use this fact to be able to extrapolate a bit or grab a bit more out of what you learn. So here, for example, what it's showing is I take this case where I say I know this information about the model. I know the linear terms. Tell me what else is in there. It fits the neural network to match what is missing from the model, and then it does what's known as a sparse regression. And sparse regression is this question of, well, if I have a function, what is the simplest symbolic equations that match this function, right? And it's then able to spit out that, a good approximation is a quadratic function, and here you go. It's actually auto-completed our model to the model that generated the equations. And how well does this work out? Well, when you try this in practice, you see that you take a bit of training data, it does this, it auto-completes the model, learns the correct model, and then extrapolates in the future in a way that looks almost perfect. And now, while that case with Block Volterra is kind of a toy example, which you can train on generated data and whatnot, which is a lab to do, you can actually go and you can take the same exact idea and apply it to real world cases, and you'll get very similar results. So here, for example, there was a case, and I'll share the paper. There's a case where the universal differential equations were used to be able to understand the LIGO black hole dynamics. And now, LIGO black hole or the black hole dynamics that were measured by LIGO. Right. And so the key really was that you do this model and you say, well, it's general to a first approximation, two black holes moving around each other are doing Newtonian physics, right? But that's incorrect, right? There must be some relativistic correction, and so you have these universal function approximators that capture what should be a correction in the model. You can ask yourself then, what is the best, what is the simplest representation of the corrected physics, and can we learn that directly from only our knowledge of the simple physics, right? And this was done by a group of researchers who did this on some of the waveform data, right? This is what I showed at the beginning there, that they used data points up for 5 to the 10 to the 4th time, and they extrapolate out entire order of magnitude more in time, and they showed that it's able to learn something that is at least close enough to being a correct model that it's an interesting model to then explore more. I do not think that they did the symbolic regression step as part of their study, right? Do you actually get, hey, what is the best symbolic representation? I don't think that they did that step for this study. That's something that I think someone can look into it and really kind of see if they can discover a good symbolic representation of this approximate model. But they at least trained the neural networks to show that it's able to learn quite well. And now you might go like, well, okay, I've seen one case on toy data, one case on real data, but is this something that we can trust? Is this something that's used places, right? Another case that came up was a case where someone was looking at building earthquake-safe buildings. Their physical model drifted over time. Their physical model is these values that for the dots here, right? And you can see that even though it kind of starts well, the physical model drifts over time. And so they did the same thing, right? They took their physical model, they augmented it with a neural network. They trained this neural network, and that's the gray, the measured data, and then the fixed, the physical model plus the neural network is then able to match this quite well, even outside the training data set. They did it in a simple case, they did it in a less simple case, and in both cases, the physical model will drift over time, but the universal differential equation approach is then able to fix the model. So there's two real world cases that have been great done. There's another case that we looked into, which was universal differential equations for battery degradation. Basically, you can use this to be able to improve the battery models that you have, right? So there's some simple battery models of how batteries degrade over time if you keep on putting them through charge and recharge cycles. But people really don't know the higher order physics for what happens, how this thing degrades. And so they learned models that would be able to do that, and they got similar extrapolation results. This was done in combustion engineering. This was done in building new propulsion devices, right? So this was a case where it was a universal differential equation with neural networks as part of a partial differential equation. So you define a partial differential equation with the neural networks in there. You semi-discretize them down to ordinary differential equations, and then you train them. This was done for filtering qubits in qubit preparation in quantum circuits. This was done for building better models of biological systems, and et cetera, right? So I'll cut off there. But basically, the idea is that scientific machine learning was new at some point, and I think that a lot of people who are students have not necessarily heard about it, because this has been all these results are from 2020, 2021, but essentially what has happened over these last few years is that this idea has really kind of shown that this using this physical knowledge does actually help. So there's quite a few validations at this point. And now the next thing that you can do is you can start to say, well, what about more methods for this? How do we start to improve the methods, and where do things go? And so let's dig a little bit deeper than just now that I've shown a few cases that scientists are using this thing, it works, etc. Let's dig into some issues of the method and start seeing how people are working through them. And the first issue with the method is if it gives you a prediction. It gives you a prediction that it thinks is absolute, right? Can we do that prediction with some uncertainty quantification? And you can. If you look at this paper on Bayesian neural ordinary differential equations, you can see that there's a Bayesian extension to the universal differential equation, which essentially does the same thing, right? Where you have some kind of function that is approximating everything that's missing from your model. You learn this, but instead of learning just the weights of the neural network in here, you do Bayesian neural network approaches. So you learn the posterior for the probability distribution of possible weights for this neural network. And every single time you sample from that, it gives you a possible solution, right? But not only that, it also gives you something cool. Like if every single time you sample from the neural network's posterior weights, it gives you a possible function that could auto-complete your model. And every single time you sample that neural network, you can do a symbolic regression on it. And so what you can do is you can actually get a probability distribution over the symbolic regression results just by running this on a whole bunch of different samples. And then you can start to see, well, there's a 95% chance that I'm missing a quadratic term and a 5% chance that I'm missing a cubic term, right? And this then starts to give you some uncertainty quantification to this approach of model autocomplete and automated model discovery. Right, so I think that one case that was interesting to look at was this case that we did for epidemic modeling. And so in this case, what we did was we noticed that, say, in an epidemic model, what you have is, so everyone knows SAR by now, right? Like you live through a pandemic, susceptible people become infected, become recovered, and this is a set of ordinary differential equations, right? But what's missing from this model is the effect of quarantine, right? So quarantine, Q of T, can put people into a state where they no longer infect susceptible individuals, and over time they will recover, even if they have the disease, right? So this is a simple model, still a simple model, right? But the key that's interesting about this model is that quarantine was very different from country to country, right? The quarantine policies in China were very strict, and in the United States, you had probably half the country that believed that the disease didn't exist and did not quarantine at all, right? So that's a very stark difference in quarantine. And so if you're to try to come up with a model of how did quarantine work, right? That model is going to be something that's extremely difficult and very human behavior dependent to understand. And so what we did was we asked the question of, let's say it's essentially a control policy, right? So people made decisions about quarantine based off of the current number of people who are infected, current number of people who could be susceptible, and how many people have recovered already, right? You look at these three details and you say, I feel like I need to be wearing a mask today, or I need to stay home today. Or, once you saw all the infections drop, you go, well, maybe I can start going back to, back to classes, or, go back to eating at restaurants, right? So we make this assumption that the quarantine policy is dependent on these other states, and so it's just some function then, right? Q is a function of S, I, and R, and so let's just learn this relationship from SIR to Q, but understand that it's going to be different country to country. And so we did this analysis where we trained this on each data. And now here's a real question, right? So this is a mechanistic model. This is a non-mechanistic term in a mechanistic model, but it should correspond to quarantine, right? I mean, that's what we think it does. So if you actually go to an independent data set, can you verify that Q actually acts like quarantine, right? So we train it on the infected and recovered data. That gives us this Q of T, right? So we train on one data set to get Q of T, and now we ask on another data set, well, can we verify that this Q of T does actually act like quarantine? And how do we verify this? We looked at newspapers for government lockdown, and we go, okay, there's a inflection point in Q of T, right, where second derivative equals 0, and that inflection point should take place where quarantine really started taking off. And so let's just graph those right next to when the newspaper said quarantine started. We train this thing country by country and see how this lines up. And you see that, within the same week, this thing is telling us that the Q of T has this inflection point. And by the magic of graduate students, you can look at the appendix and see, but country to country to country to country. I think that there's 160 countries this was analyzed on. I think that the average difference between the inflection point in Q of T and the data point was about like 4 or 5 days or so, basically saying that maybe it takes a bit of time to ramp up quarantine, but this really is learning something that is mechanistic, right? And so this is one interesting thing that comes out of scientific machine learning, is that you can do machine learning, but you still have terms that your terms are still within mechanistic models, and so if you try to interpret them, the interpretations do seem to be something that makes sense with respect to how you're measuring them. So another thing that came up, though, is this question of, well, when we do scientific machine learning, right, we have this neural network bit, and then we have information bit, and when we put the two together, we hope that this is easy, this has more information than just using the neural network itself. Can we verify that on the case of a universal differential equation? Right, so here we take this to a case where we do that. Right, so here we go to these epidemic models with all this epidemic data, and we show case by case by case that indeed that is the case. So, what is a neural ODE? A neural ODE is just U prime equals a neural network. So that's with no physical model involved. And then here's the QSAR, right? This kind of quarantine SAR, right? So it has a neural network in there, but it's still a epidemic model. And you can see that if you give it this data, this red data, and you tell it to extrapolate in the future, the one that has more prior information extrapolates much, much better than the pure neural network form. And does that in that case, it does this in every case, right? So, we have a paper that's just kind of going through and just kind of showcases that, as you put more prior information in, you need less data to get the same amount of measurement error, right? But I think that there's a few other things that are interesting to read off of this, right? That's the very basic thing to read off of it, but there's a few other things here. So, for example, when you look at these kind of differential equation models, right? You have S move to I move to R, I move to T moves to R, right? There's a natural conservation of person in here, right? So it's when these differential equations have a conservation in them, right? Because what is the rate at which S goes to I? It's S, it's S type beta times S, right? And because of that relationship, right, as S goes to 0, this will, as S goes to 0, the rate of this reaction goes to 0, right? That's your standard thing that happens in first order chemical kinetics kinds of equations. And because you have that relationship, you can actually see it inside of the machine learning results, right? That QSR will always have S plus I plus R plus T equal to 1, no matter what the neural network is, because that's a property of the solution to this differential equation. And so it will learn, so basically it needs to learn that, but also we don't have recovered become susceptible in this equation. And so what you can prove if you look at this equation is that you can prove that there has to be one point in time where there's a maximum to it. And so what the QSIR is having to learn is, given these two constraints, right? So given that the number of people always adds to 1, right? And given that there has to be one maxima in here, please find out how to extrapolate. And what do you know? It extrapolates quite well, right? And the neural ODE, on the other hand, can be any possible differential equation. And so you can see that it's violating some core tenets right there, because when it extrapolates, it says that the number of infected individuals is going to be above 100%. So more than 100% of people are going to become infected by 80 days. And so you're like, that's impossible, right? And so by really another way to think about what this kind of scientific machine learning approach is doing is it's constraining the possible functions that can be learned, right? It's constraining the behaviors that can be learned to be things that you know have to be true. And by adding constraints that you know have to be true, you end up with a simpler problem of finding the correct function from those constraints. Now, to kind of transition towards software and the mathematics part of it, I want to look at one last case of scientific machine learning, which is using scientific machine learning to accelerate the simulation of ocean columns. So in this case is, here's fluid flow. It's a three-dimensional Boston-Hess approximated Navier-Stokes equation. And what you want to do for climate models, you want to take a box of water and you want to essentially just find out how to turn that into just an equation that tells you how temperature flows up and down in a column. And then you just want to have a bunch of ocean columns, you just stack them nearby each other. And a climate model is just a bunch of one-dimensional ocean columns standing right next to each other, right? So you want to kind of get rid of this XY behavior. So how do you do that? Well, you take an integral along the xy plane, you approximate it, you then take just the first term in your Taylor series, and that's a decent approximation, right? That's the normal way you approximate in physics. And if you do that, you get everything in this equation except the neural network. This is called the convective adjustment. It's what's used in climate modeling of today. And so when you do that, when you do the convective adjustment, you find out that you're missing something, and so you can say, okay, well, let's, all these terms that I would have dropped off, like the extra terms of the summation, these higher order nonlinearities that in a physics class you normally just say are O of delta x cubed, so 0. Instead of making them 0, let's make them be a neural network, and let's actually just try to approximate the terms that we're dropping off, right? And so this is a neural network-based closure approach with the universal differential equation. And what you can see when you do this, well, okay, so how do you actually train this neural network? I've completely skipped over how you train this thing so far. Well, what you can do is you can take your data set here and you can find out what the heat flux is going up and down at every single point in space. You can then then take the derivative of those and be able to just get a data set for what is, how is the convective adjustment equation, how incorrect is it, right? The convective adjustment's residual against the original data set is what the neural network should be matching. And so you just train the neural network to match that residual, and then you stick it in your simulator, and this is what you get. And the two lines are not on top of each other, so scientific machine learning has completely failed, and you say, okay, it does not do as well as I want. Why? But the real question is, I just described a way to train this neural network. Is that a good way of training? And it turns out that it's not. And the reason is because this is trying to to get the derivative correct, right? So you're pulling this neural network out in isolation, and you're seeing, okay, can I get this neural network? Can I make this residual correct? And after training the neural network, you put it into the differential equation, and you get a drift because you've only controlled the derivative to be correct, and a controls engineer will instantly yell at you and say, you will always get drifts in your solution if you only control the derivative. What you need to do is control the integral. So here is integral control, right? We have the same equation here, right? And instead what we're going to do is we're going to solve the differential equation with the neural network in there. And we're going to solve the differential equation, and we're going to take, so we're going to use the solution of the differential the points, the temperature at each point in space, and we're going to use the solution of the differential equation with the embedded neural network in there. We're going to take the loss with respect to those two. Right. In the first case, you train the neural network outside and then you stick it in. In this case, you actually train the neural network as part of the simulation process. And this actually gives you about 4 orders of magnitude less error. So what this tells you is that you cannot do this in a way where you train a neural network and then you stick it into a simulator. You actually need to have the entire simulation process as part of the neural network's kind of training procedure. And this is where we start to look at, okay, well, how do you train such a loss function? Then you need to differentiate the solution of this PDE with respect to the weights of the neural network, because if you want to do gradient descent, that's the gradient of this loss function, right? So we need to be able to differentiate simulators, and that's where this whole problem of differentiable simulation comes in, right? So what we need to do is we need to then solve this problem of, well, how do you differentiate simulators effectively?